Hello and welcome back. In this video we'll be looking at section 9.1 and this is getting into testing two proportions at the same time. So in chapter 8 we saw that we can test whether or not a proportion is equal to a particular number. Here we're going to be testing whether or not two proportions could be equal to one another, or maybe less than one another in some order. Maybe P1 is less than P2, or P1 is greater than P2. So we've got two different populations, and we want to compare some proportions about them. So it could be something from maybe our two populations that we're looking at are going to be, say, men and women in the US, and we want to test if they have the same, say, proportions of prevalence of some diseases. Or we could be flipping two coins or rolling two dice and seeing whether or not they land heads, or you get a 6 on both of them at the same proportion. So what we'll need to do is test both populations by taking two samples. We'll take a sample from population 1 and a sample from population 2, and we'll have a bunch of statistics to work with. So here is just a brief outline of all the notation that we'll see. So P1 and P2 are the actual proportions within population 1 and population 2. These are what we don't know. These are what we're trying to test. When we take a sample, we will have a sample size for both populations, and then within each sample we'll have a certain number of successes. So x1 is just how many successes we get out of the sample from population 1, and x2 is the number of successes from the sample from population 2. P1 and Q1 are just the proportions of successes in population 1 and the proportion of failures. And ultimately, we would suspect that P1 should be P1 hat should be close to P1, since our samples should be representative of the overall population, but we don't know for sure. And again, we have the same things over here. The one thing that we will do that's maybe slightly different than just having a one population test is we'll have what's called a pooled statistic. And the pooled statistic will take our number of successes from both trials and our sample size from both trials and turn it into sort of an overall success rate, and then an overall failure rate for Q as well. This is just used in some of the calculations. It doesn't necessarily have a good meaning outside of that. So in order to test whether or not two proportions are going to be equal, there's a few things that we need, and these are pretty standard. Our samples from both of our populations have to be simple random samples, just like always. One thing that's maybe a bit different is that our samples have to be independent. We don't want to use the sample that we collect from one population to influence the sample that we're collecting from the other. They have to be totally independent of one another. We don't want them to affect one another. And again, like usual, we will want that when we are taking these samples, we want at least 5 successes and 5 failures. If either the successes or failures are too small, it means that we haven't sampled a large enough pool from the population. So those are just the 3 standard requirements. And when we are testing proportions, we normally, our test statistic is normally z, because we will assume that it's going to be like a normal distribution, and z is the common variable that we use for a normal distribution. The test statistic is essentially, we want to look at the difference between how far apart are our samples versus how far apart do we think the actual population are. So P1 hat minus P2 hat, that's the difference in the sample proportions. P1 minus P2, that's the difference in the population proportions. So we're just trying to see, are these actually different, or are they the same? And the null hypothesis is when we set our parameters equal to something. Well, in this case, the only way that they can be equal to something is if they're equal to one another. We're not testing whether or not they are equal to some other number. We're only testing them in relation to each other. So the only way that we can have an equal sign is if they are equal to one another. So this is the only null hypothesis that we'll be testing. And I think that this is all very similar to the material in Chapter 8, where we're looking at testing single populations. So what I'm going to do is I'm going to dive into an example, and we'll go through it in exactly the same way that we were doing this before in Chapter 8, and I'll just mention where this will be different. So let's say that we have two quarters, and we want to see whether or not they land heads at about the same rate. So we flip both quarters 100 times. Quarter 1 lands heads 49 times, quarter 2 lands heads 53 times. Can we claim with a significance level 0.1? Note that if we're only testing quarters, it doesn't have to be a very high significance level. So this is something that we don't mind using 0.1 as opposed to 0.05 or 0.01. And then can we claim that the two quarters have different probabilities? Because, well, clearly they landed a different number of heads. One landed 49 times, one landed heads 53 times. But is that really all that different? Or are they close enough that they could land with the same probability? So first of all, the claim, well, it's just spelled out for us. The quarters have different probabilities of landing heads. And sort of symbolically, what this means is that the two probabilities or proportions that these quarters will land heads, P1 and P2, symbolically we're saying that they're just going to be different, so they're not going to be equal to one another. So far it's just like normal. The null and alternative hypotheses. Again, the null hypothesis is when we assert that things are going to be equal to one another. So in this case, P1 is just equal to P2. And the alternative hypothesis is just going to be that P1, again here, is going to be not equal to P2. If we were wondering if one proportion was bigger than or less than the other, then that would be our alternative hypothesis. In this case, we're just wondering if they are equal or not. So we don't care if one is bigger than the other. So we'll have just not equals there. And our significance level, we said, is going to be 0.1. And again, if this were medical trials, something like that, we would want a much smaller significance level so that the chance of an error is a lot lower. Here, we don't really care if we're all that wrong when we're just testing whether or not quarters flip heads at the same rate. So our test statistic, which I have the formula written down here again, there's a few things to notice here. One is that a few of these variables we can calculate pretty easily. So N1 and N2 are just the size of our samples. Well, we flipped both quarters 100 times, so that's pretty easy. P1 hat is just the proportion of heads in our first sample. So that was 49 out of 100, which is going to be 0.49. And P2 hat is going to be the proportion of heads in the second sample. So we flipped heads 54 times in that second sample out of 100. So that's going to be 0.54. And then P bar and Q bar were the pooled statistics. So what we do is we take the total number of successes out of both samples and divide it by the total numbers of things sampled. So here we have 49 plus 54 is 49 heads and 54 heads out of 200 flips in total. So this is what, 103, and if we divide that out, I think we get 0.1, sorry, 0.5, but a little bit more, 0.515. And then Q is just going to be 1 minus P, Q bar is going to be 1 minus P bar. This is going to be 0.485. So we can come up with all these guys, we can plug them in, and we get Z is going to be equal to negative 0.7074 after we round to 4 decimal places. Eventually, I will show you that this can be easily calculated in StatCrunch, but for the moment I want to do things a little bit by hand. So this is how we come up with our test statistic. Now, you're probably wondering, okay, we know what P1 hat, P bar, Q bar, we know all of these guys. The one that we don't know is this one over here. P1 minus P2. Now this is the actual population of, the actual proportion of heads from quarter 1, and this is the actual proportion of heads from quarter 2. But we don't know these. But what we're doing is we're testing whether or not they are equal. So this is our null hypothesis, that P1 is equal to P2. So P1 minus P2, if those guys are equal to one another, that makes this 0. So this is our big sort of assumption going into all of the hypothesis testing, is that P1 minus P2 is in fact equal to 0, that these are equal to one another. So why didn't I mention this? Well, it's just 0. So we just get to ignore it. Anything minus 0 is just itself. So what I did is I plugged all these values in for everything here, and for this guy, this was just 0. So here is our test statistic, and now we need to find our p-value. So again, with our p-values, we're assuming that everything is normally distributed, and with a standard normal distribution, we've got 0. So negative 7.74 is going to be what, about right here. And to find the p-value, we want to find the area outside of this guy. However, this is also a two-tailed test, meaning that what we're doing is we're testing whether or not P1 is equal to P2. So it could be that P1 is just not equal to P2 because P1 is a lot smaller than P2, or it could be that P1 is a lot bigger than P2. So let's come over to StatCrunch, and we can go to our calculator and our normal distribution calculator. Our standard normal distribution has mean 0 and standard deviation 1, and our z-score is negative 0.7074. So the area to the left over here is going to be 0.2396. Let's keep four decimal places, but I have to round, so that's 0.2397. So that is going to be the area down here, 0.2397. But it could be that P1 is a lot bigger than P2, in which case we have the same area up here. This is going to be 0.2397. And our p-value is in fact going to be the sum of these two guys. So I'll just have to do a little bit of addition in my head. I didn't write this down beforehand. So our p-value is going to be 0.4794, the sum of both of these guys. And when we're looking at whether or not we reject this, well, this is clearly a lot bigger than our significance level, so we fail to reject. It is not unlikely that our 2 quarters got a heads 49 times and 54 times, but they could have had the same probability of landing heads.